So here is another example on how to use the Henderson-Hasselbach equation in buffer preparation. This time, we will consider a very common buffer system used in biochemistry. So a student wants to perform a biochemical experiment at pH 7.4. He found the following recipe online. Can the student use this buffer for his experiment? So we have 25 grams of potassium hydrogen phosphate and 12 grams of potassium dihydrogen phosphate in 250 ml of solution. So again, the first thing you need to do is to identify if you have the correct components for your buffer. You have to be familiar with your acids. So you should be able to recognize that we have here hydrogen phosphate and dihydrogen phosphate, which is part of uh, a series of dissociations by phosphoric acid. So let me write down first the dissociation reactions of phosphoric acid starting from the very first. So we have phosphoric acid. This forms dihydrogen phosphate plus what? The hydronium ion. Next, your dihydrogen phosphate also dissociates, and this forms hydrogen phosphate and of course hydronium ion. And lastly, your hydrogen phosphate dissociates, forming phosphate plus hydronium ion. And each of these step has its corresponding Ka. So for the first step, the Ka is equal to 7.1 times 10 raised to negative 3. The second step is the Ka for the second step is equal to 6.3 times 10 raised to negative 8. And the Ka for the third step is equal to 4.5 times 10 raised to negative 13. So the corresponding pKa values for this, so for the first one, it's 2.15. The second one is 7.20. And the last one is 12.35. So you should be able to see that from this recipe, the equation that should be the basis for the computation is the second dissociation reaction. So you have the components in the recipe, right? So you have dihydrogen phosphate. So this will come from this reagent, KH2PO4. And we also have HPO4 or hydrogen phosphate from K2HPO4. So which is our conjugate base? HPO4, 2 minus, hydrogen phosphate. And our weak acid is dihydrogen phosphate. So our Henderson-Hasselbach equation will look like, so we have pH equals, the pK that you will use is the pK for the second dissociation. So that's 7.2 plus logarithm of, again, the conjugate base is hydrogen phosphate, and the weak acid is dihydrogen phosphate. So now Since we are given the masses of the reagents and their corresponding molar masses, we can compute for the corresponding concentrations of each. So let's start with the conjugate base hydrogen phosphate. So again, this will come from this KH2P. This one will come from K2HPO4. So we have 25 grams of K2HPO4 divided by the molar mass 174.18 grams per mole. And then this one is moles of K2HPO4. So I have 1 mole of K2HPO4. For every mole of this salt, I have 1 mole of HPO4 2 minus. And then we divide this by the given volume of the solution, 0.250 liter. So the value for this is 0.5741 molar. For the weak acid component, we have dihydrogen phosphate, which will be coming from the second reagent mentioned in the recipe, KH2PO4. So we have 12 grams of KH2PO4. We divide this with the given molar mass of the substance, 136.09 grams per mole. And again, just to make this clear, we use a conversion from the moles of the reagent to the moles of our weak acid. So we have 1 mole of KH2PO4. In 1 mole of this substance, you have 1 mole of dihydrogen phosphate. Then divide this by the total volume of the solution, 0.250 liter, and you will get a value of 0.3527 molar. And now we have the concentrations of the two components, and we can plug them into our Henderson-Hasselbach equation. So 7.2 plus logarithm of 0.5741 molar divided by 0.3527 molar. And you will get a pH of 7.41. So to answer our question, can the student use this buffer for his experiment? The answer is yes. He just needs to adjust the pH using hydrochloric acid. So for the pH to go down from 7.41 to pH 7.40.